After just 1 mile, there should already be 8 inches. After 2 miles, 32 inches. And after 3 miles, there should be 72 inches, or 6 entire feet of physical curvature between point A and point B. Taking my trusty Nikon P900 Ultra Zoom camera, we traveled to Highland Lake to perform our own experiment. From one end of the lake to the branching midpoint is almost exactly 3 miles, giving a perfect camera position and target observation area. Unfortunately, due to the angles of the lake and trees, 3 miles was the maximum I was able to see. Does it appear that the water at one end of the lake is 6 feet lower than the water at my feet? We shouldn't even be able to see the opposite shoreline, if that was the case.
That was flat earther Eric Dubay trying to convince you that the world cannot be a globe because he's misunderstood what 8 inches per mile squared was all about. Of course, it's completely the wrong thing to use when you want to know how much of a distant object should be hidden behind the horizon. So Eric had a target distance of 3 miles, and his camera was at least 6 feet above the water. Using 8 inches per mile squared, all he could do was input the surface distance s. 3 squared is 9, multiply that by 8, and you get 72 inches, or exactly 6 feet. And that's obviously the wrong answer for any hidden amount, because nothing of a target would be hidden when the target is on, or completely in front of, the horizon. What about an observer who is at 20 feet, viewing a target that's, say, 50 feet tall, 10 miles away? The correct formula allows for the observer height, the target distance, and it also includes refraction. This tells us there should be almost 10 feet of bottom-up obstruction, which means 40 feet of the target should still be visible. But when flat earthers use the 8 inches per mile squared rule for the purpose of finding out how much of the building can still be seen, then they'll wrongly conclude the entire building should be hidden behind the horizon. So this was part 1 of a series of maybe 8 short videos, where I'll be using GeoGebra to explore these formulas, and I'll also be trying to bridge the gap between the globe and flat earth models using 8 inches per mile squared. So brush up on your trigonometry and come and join me for part 2, where I'll be taking a look at what Eric should have been using, and that's this formula for hidden height. Catch you later.